Sequence retrieval. So you have a sequence at hand, something we call a query sequence. This may stem from, say, a sequencing project or similar. And now you want to find this sequence's closest homologs in a sequence database. You then know that you will need an algorithm that's really quick. You know that you're probably going to search quite a lot of data. The databases are these days quite large, and hence you need something that operates quickly in order to make yourself not having to wait too long. As well, want it to be accurate for mostly the same reason. Many hits to a sequence database will also mean that it's become very hard to distinguish signal from noise. So you need something that's very accurate. You also need something that gives you significance as an output. So an algorithm that could tell you how likely does this finding that you find, or this homolog you find, how likely is this just random noise, and how likely is it a real match. You know this from Googling yourself. Sometimes you find just random noise when Googling sequences or random Googling sentences. Wouldn't it be great to have a measurement of how relevant your finding in the database is to what you were asking? These sort of three different properties is something that we will have in a search algorithm called BLAST that we will walk through a little bit later on in the lecture. But in order to get you to that search technique, I will have to go through a couple of concepts before. First, sequence databases. Most information stored as sequences are stored in so-called FASTA format. This is a simple text file format, and it's been around for a very long time. That's why it's popular. It is as well very simple. It simply stipulates that you start each sequence entry with a greater than sign followed by its name. Then you take a new row and you write your sequence after. Here's an example. These are a couple of entries out of the Uniprot entry. It begins with firstly a greater than sign followed by a sequence. And you will see in this particular case, actually the name takes up multiple rows, but there's actually no row break in between. It's just as a period on the screen. This format is valid both for protein sequence, as this case is, where we see the different amino acids on top of each other. And it's valid as well for DNA information. So then you see bases, four bases in after each other. Sometimes you see that there's line breaks. Sometimes you see spaces in between the different characters. Everything goes when it comes to formatting of FASTA database, as it's not really well defined. However, this is an extremely popular format, and you will see that most of the sequence information is stored this way. Another concept that we need to walk through in order to get to where we want to get with this lecture is so-called k-tuples. K-tuples are short stretches of sequence of length k. They are a good way just to divide a longer sequence into shorter morsels. So, for instance, you can divide the sequence into 7 different free tuples: ASE, SEQ, EQU, QUE, QEN, ENC, NCE. So by dividing things into k-tuples, you will now get sort of shorter length representation of this little longer sequence. This concept could be used when we want to index FASTA databases or other sequence databases. In general, searching structured information is much faster than searching unstructured data. So here the concept of indexing is something that can greatly speed up searches of unstructured data. And the way we index inside of sequence databases are k-tuples. So here we have an example I have made with free mirrors. So you could sort of divide up each of these sequences into free mirrors, and you will then be able to store pointers from each of these free mirrors, so that you store in a separate index, and that reference now into the sequence itself. So for each free mirror, there's sort of a pointer to where it occurs in the text, and note that this could be in multiple different locations in the text. With these concepts covered, I can now transition over to what I really want to discuss, and that's the basic local alignment search tool, BLAST for short. It's a very well used tool. It's actually one of the most cited papers in bioinformatics, if not in all of science, actually. And it's sort of a way now to heuristic to create a local alignment that links a query sequence to all the entries in the database entry, and trying to find the most close homologue. It's sort of using this idea with k-tuples, and it's sort of it's a parameter that you can use to tune BLAST, but typically must select k somewhere between 3 and 6 for proteins, and maybe between 6 to 20 for DNA sequences. The algorithm that it's executes is sort of straightforward. You just divide your sequence into k-tuples. You expand the list of k-tuples to any k-tuple that match within the alignment score larger than a certain threshold t. So you had sort of a certain length of list, then now you expand it to a larger list. Then you scan the index for all sequences that match this expanded list. And for each of the matching sequences, you extend these matches. So this is these extended matches, they are called HSPs, or high scoring segment pairs. And finally, you calculate the significance of each of these HSP. Two of these steps probably need a more close explanation. Firstly, how do you extend the k-tuples? If you plot the query sequence versus the database hit that it makes, the sequence in the database, you will see diagonal lines here in the k sequence where the two sequences match. What you can do subsequently is to try to extend any matches so that they sort of match each other between the different positions. You will note then that diagonal lines that can be extended, they might render a higher score than sort of spurious matches that are not connected to each other. The last step also as well involving calculated significance of a score. This is probably the greatest achievement of the BLAST algorithm, but it is that they can calculate the significance of any match. This is enabled by something known as the Karlin-Altschul statistics. It stipulates that you can calculate the value E That's equivalent to the number of sequences that get the local alignment score greater or equal to S. And this just by executing this formula here, where now S is the score that we have achieved, and M and N are the length of the query sequence and the summed length of all these sequences in the database. And the parameters lambda and k are estimated for each score matrix and database. So there are actually a certain tuning phase of BLAST, which you can where you use random alignments just in order to see what values to select for lambda and k, given the size of this database, given the database at hand and given the scoring matrix at hand. This value E is known as expected value, or sometimes E value of an HSP. It's sort of equivalent to how many sequences would I expect by chance to match as well as it does, as this HSP does. A E value of 100 would mean that 100 sequences would get as good sequence, or 100 sequences in this database would give us good score as this particular one, even if it was a random chance, just by random matching. So this is probably not a good match. However, E value of 10 to the minus 10, for instance, would say that this is a very rare event that you get a match as good as this one. Hence, you tend to trust those. Thank you.